In the last few sections, we talked about congruent triangles, some ways in which we can prove them, and about there's certain parts of the triangle that makes them congruent. If we look at the triangles XYZ and triangle MNO, and we state they are congruent, do you know that segment MN is congruent to XY? The answer would be yes, because as we know, if two triangles are congruent, we know that all three angles along with the sides are congruent. So there are actually 6 parts. What this is it's called corresponding parts of congruent triangles are congruent. We can shorten that by cpctc. And what this is if we state that the two triangles are indeed congruent, that every single part of them are also going to be congruent. The next topic that we'll talk about in this section are circles. In this book, they're going to label circles by the following. A picture of a circle with a dot in it, followed by the name. Usually it's a variable, capital letter. What that does is it names the circle, and A is considered the center of the circle. The center names the circle, but is actually not a part of it. The center helps generate the outer edge of the circle, and it does so by the radius or radii, meaning multiple. AM would be considered the radius, as would AN or AO. If you have multiple radius, it's called radii. Notice the distance of each radii, AM, AN, AO. You'll notice that they will be congruent. This happens in all circles. And that brings us to our next theorem, that all radii of a circle are congruent. A couple of things also to remember about circles as we're going through this chapter. The first is that the area of a circle can be found by using pi times the radius squared, and the circumference can be found by 2 times pi times the radius. Let's look at a proof type problem on page 128, number 14. This proof is going to use cpctc, corresponding parts of congruent triangles. If we look at the givens, we're told a few things. The angle 5 is congruent to angle 6. Angle JHG is congruent to angle O, and that GH is congruent to MO. What we're trying to conclude is that angle J and angle P will be congruent. Now, since they are in separate triangles, as you can see in the diagram, the best way to do this would be to prove that the triangles are congruent. Therefore, that the corresponding parts, which include angle J and angle P, are therefore congruent. So we're going to have to think about how we're going to get those two triangles congruent. As with most proofs, we're going to start with our givens. That angle 5 congruent to angle 6, angle JHG congruent to angle O, and segment GH congruent to MO. Now, if we go back to the diagram and look at the triangles that we have, we've established angles congruent. We've also established a pair of sides being congruent. So knowing about the postulates that prove congruent triangles, our best option is to try to get either side JH congruent to PO, or angle JGH congruent to MPO. You do this by looking at the diagram and what's given and to figure out what would be easiest to find congruent. My suggestion is that JGH being congruent to PMO is going to be the easiest thing to prove congruent, since we already know that angle 5 is congruent to angle 6. We can start by saying that angle 5 is supplementary to JGH and angle 6 is supplementary to PMO. By doing this and knowing that 5 is congruent to 6, we also know that those angles JGH and PMO will be congruent, because if two angles are supplementary to congruent angles, then they are congruent. Once we establish that those angles are congruent, we now have enough information to prove that the triangles are congruent with angle-side-angle postulate. Since we now know that the two triangles are congruent, we know that every single side and every single angle within that triangle will be congruent, including what we're trying to conclude, that angle J is congruent to angle P. And again, our reasoning will simply be corresponding parts of congruent triangles are congruent. And again, you can shorthand that with cpctc.